Good morning, everybody. So how is everyone doing? Hopefully I'm seeing a lot of nods. All right, thumbs up, good. All right, excellent. So can people in the back hear okay? Awesome. All right, so today we're here to talk about one primary thing, and that is essentially using a slide advancer. Darren can, I believe so. All right, let's try that again. All right, perfect. Okay, so today we're here to talk about one thing. Primarily, it's the concept of using cloud to get better answers faster. So this is centered around the area of technical computing, and the way I'm from Cycle Computing, I'm Jason Stowe. Essentially, the way we think about technical computing is that it's a mix of several different things. Essentially, simulation and analytics workloads. So traditional HPC, I worked at the Pittsburgh Supercomputing Center in the early 90s on a Cray T3D. So this includes your very parallel MPI-oriented workloads. It also includes more throughput-oriented workloads like design optimization. And we're going to talk about a couple of instances of that today, as well as analytics and what might be traditionally called big data nowadays. So at Cycle, what we believe is that getting easy access to cluster resources is the single largest accelerator of invention and discovery over the next couple of decades. It's a case of the haves and the have-nots. Now everyone can get access to an exceptionally large amount of compute power at reasonable cost. And anytime that happens, whether it's a printing press or cloud computing, you get a renaissance of ideas and computation and science, and we're really excited about that aspect of it. So cluster computing is actually everywhere. So if you're the CEO of Novartis, Joseph Jimenez, and you go up and tell Forbes that you're going to bring a cancer drug to market 2 times as fast by the end of 2016, cluster computing is actually one of the things that gets you there. So you cannot do that without actually running the genomics workloads, the clinical trial simulations, the docking runs, all of the drug design. It provides traditionally strategic answers to many of companies' most important questions, and in the process actually gives you speed and agility. As the next topic, I'm just going to talk a little bit about Jevons. This is William Stanley Jevons. Like many people in the 1800s, he looks like he's from Brooklyn, or is going to code a social media app. But in the meantime, he was in the UK in the 1860s. And at that time, they believed 2 things that were incorrect. Number one, we need a fixed amount of steam power. And the corollary to that if we make it more efficient to create steam power out of coal, then we will use less coal. And these both turned out to be incredibly wrong. So as you increase access, decrease the cost, you actually use more of something rather than less of it. And that's essentially what's going on in computing as well. So in technical computing, we're all used to, or at least I was for the first many years of my career, used to sizing the question to the cluster that I had. And in the case of coal in particular, we actually have been using more every year than we have, more every year since the mid-1860s than we did the year before. So as a result, Jevons Paradox is actually playing itself out relative to cloud computing capacity as well. Fixed size clusters are too small when you need them most and too large every other time. I think I've said that one sentence every year at reInvent for the last 3 years, so it was worth saying it one more time. But the fundamental concept's the same. So when you're using your cluster, wish you had a larger one. When you're not using your cluster, you wish you didn't spend as much on the infrastructure. Cloud obviously addresses this, but moving workloads is hard, and that's essentially what Cycle seeks to do. We want to make it very easy to take these workloads and scale them out. And in the Novartis example that I gave earlier, in July of this year at the AWS Summit in New York, Steve Litster got up and talked about a 40-year drug design that ran in 9 hours. They found 3 compounds, that are potential drug candidates. That's a grand slam home run in that industry. For $4,372 in spot instances. And we essentially helped with 3 things: burst, the data workflow side of getting the data there, and the orchestration of the 10,000 server environment on AWS. So again, thanks to cloud, we can now ask the right questions, the ones that will actually change your business, change your research, and not the ones that fit on your cluster, and use this extra capacity to get better answers faster. And that's really what we're talking about today. So we're going to talk about one use case, which is record scale. Another that's enterprise speed. We have two speakers, Patrick Saras from USC and David Hines from HGST. They're both doing very innovative work in accelerating their respective workloads. Both of them will highlight, again, asking this notion of the best question and not the one that fits on your cluster. And with that, I'd like to introduce Patrick Saras, who's going to talk about designing better solar materials with big-scale computing.
Thanks, Jason. Thanks for the introduction.
Thank you.
Good morning. So I'm Patrick Saras. I'm a chemist. I'm a synthetic chemist. I'm not a computer scientist or anything of the sort. So I'm hoping that today I can give you a little bit of a taste of what we're doing in terms of research and how scientists like me are thinking about using large-scale computing. It's been fun to talk to some of you at this conference because I had no idea. It blows me away the kind of code and software that keeps something like the cloud running. But when you plug in your laptop here at the conference, on average in America, your laptop still is powered predominantly by the combustion of fossil fuels. 1/1000th of the charge in your laptop battery is from solar energy. So we are using chemistry to try and address this problem. We think that we can do better and that we can upgrade our energy technology to match our information technology. So it's not that we don't know how to produce energy from sunlight. We actually, with silicon solar cells, we're able to do that in a very efficient way. Our physicist friends tell us that silicon solar cells operate at near the theoretical limit for such a process. But why don't we have more solar? And the reason is that solar requires a large upfront investment. So silicon solar cells are big, they're heavy, and they're very expensive. It takes a lot of, there's a large inertia to switching over to silicon technology. Excuse me. So we believe that we can solve this problem by using the organic solar cell. The organic solar cell is a thin layer of a light-absorbing dye, and it promises to be thin, lightweight, and very cheap. Think by analogy to when computers were only made of vacuum tubes and relays, and somebody would have said that all of us carry a computer around in our pockets. The realists in the room would have said that's impossible or not feasible because computers are too big, they're too heavy, and they're too expensive. So we need the personal computer of solar cells. I apologize for the colors, it's coming out a little bit strange. But let me take you down to the microscopic level of what an organic solar cell looks like. In these thin films, there's actually 2 layers of light-absorbing dyes, each one much thinner than the thickness of a human hair. They're a few nanometers. One is a material that, when it absorbs light, likes to accept an extra electron from its surroundings. And the other is, as you can imagine, one that, when it absorbs light, it likes to give up an electron to its surroundings. So we aptly name those an electron acceptor and an electron donor. When light shines on the device, the donor gives an electron to the acceptor, and that electron is collected at the negative electrode, forming a current in the circuit. So to get further into it, as chemists, we need to decide what is it that makes something an electron acceptor or an electron donor. So I'll zoom in even further down to the molecular level. The electron acceptor that works very well is a soccer ball-shaped molecule that you've probably heard of called a buckyball. It's an all-carbon 60-atom soccer ball shape. It's a fantastic acceptor, actually. It really likes to accept electrons from its surroundings. One of the things we use as an electron donor, one of many, is this molecule called pentacene. It's penta for its 5 rings of carbon. And that's going to come back because that's one of the molecules that we're looking at dealing with. So I told you about the buckyball being a really nice acceptor and that pentacene is a donor. But unfortunately, the device as drawn is not that efficient at all, actually. It has a really low voltage. And what we need to do as chemists is not just change the device structure, but actually change the materials that make up the device. There's many, many different materials that you could use. The primary requirement, though, is that they have a color, right? A transparent solar cell isn't doing you much good. Good solar cell is black, actually. That means it's absorbing all the light. So we look around us and think, what things have color? So pentacene that I told you before is kind of like pentalead. It's a small fragment of graphite. Chlorophyll is drawn there. That's the green stuff in plants that's doing photosynthesis. And I've even shown the structure of indigo, which gives the characteristic blue color to blue jeans. So The process of taking a molecule all the way through to a device and testing it and determining if it's a good material or not starts sort of on this roadmap at the top left. We stand around at the whiteboard drawing structures, putting our heads together, drinking coffee, and staring out the window, thinking, what is the next great material going to look like? What is the chemical structure? This process is based on intuition more than anything. We use our collective knowledge as chemists and our sort of gut feelings about, we think this structure is going to perform well in a solar cell. Moving on from that, we go into the lab, and this is my specialty, this is what I do, is the chemical synthesis. But it's a real bottleneck in the process. It can take months to years to synthesize these materials. There's no cookbook and there's no recipe for something that's never been made before. Once we do figure out a way to make it, we now take what's probably the world's supply of this material into our device fabrication lab and actually make the solar cell. From there, we take it into our testing and analysis lab and determine what properties have changed from the last material, what have we learned from making this material, and we kind of cycle that back into doing the target selection, using what we know from the previous run through to develop the next great material. But like I said, this can take months to years to go around this cycle. So ultimately what we get is maybe after 3 years, 3 data points. And it's really hard to go back to the target selection and decide, where are we going? What is the trajectory here? So we think that large-scale computing can change this by putting our data in context, even if the properties that we predict are of materials that we'll never make, and we might not have a way to synthesize the predicted materials. It still gives us a larger landscape, a roadmap for what we're doing. It really helps to inform our intuition as chemists so that when we're doing target selection for the next material, we can base our hunches and sort of ideas on some sort of basis that is in the computation. Ultimately, this helps us to ask the right questions about what properties do we actually care about in a material. We think we know what makes a good solar cell, but that idea is changing all the time, and these calculations help us to zone in on which properties are of interest to us. So let me talk to you in a little bit more specifically about the MegaRun, this large-scale computation that we did. Jason will tell you a little bit later about the actual the coding behind it and how it ran on the cloud. But I'll show you how we come up with lots of molecules in a new way, right? So let's take pentacene and imagine I do some mental chemistry. I take 4 of the carbons and I replace them with nitrogen. There's 135 ways to do this in pentacene. That's all the structures that have 4 nitrogens substituted in. This is part of a study we did on a smaller scale with our collaborators at Schrodinger Incorporated, Matt Halls. He put those 135 molecules to the test, and the data is plotted here. I won't go through it too much, just suffice to say that the vertical axis is something that tells us something like how easy is it to put an extra electron onto these materials. So the materials towards the bottom are easier to put an electron on, so they would be electron acceptors. And you can see a dotted line across where the buckyball stands. And in the top right corner is pentacene. It's a lousy acceptor, we know that, because it's a donor. But by putting 4 nitrogens in, we've made it more electron accepting, and in fact 4 of them are more electron accepting than the buckyball. Problem is, I can't make any of those 4. I have no idea how to even begin to make those materials. But it tells us something about there's a way to substitute nitrogen in that makes an electron accepting pentacene. But 4 data points isn't enough to do it. I can't tell you what's special about those 4 out of the other 135. So what we need to do is to increase the size of the library so we can start to really get an idea of the lay of the land. To get from hundreds of structures to hundreds of thousands of structures, we need to play the game a little bit differently. So we took a parent structure that looks kind of like pentacene, it's almost the same, and we started by playing that same game of substituting nitrogens in. So we put some nitrogens in, and that generates anywhere between, we put anywhere between 0 and 5 nitrogens in, and that generates about 3,500 structures. We then decorated the outside of the molecule with something called a phenyl group, and that gets us up to 500,000, which is really a large library. We took a third of that library and ran it on the cloud with the help of cycle computing. We got 201,000 data points back. These are numbers that are really hyperbolic to chemists. We're not used to dealing with this much data. This is kind of new to us, especially in materials chemistry. For example, to calibrate you, The American Chemical Society gives a number, they give an identification number to every material and chemical that is known in the scientific literature. They keep a running tally on their website. It's about 90 million right now. So in a day, we calculated close to the order of the total number of molecules known to science. And that's really amazing to us. So this is what 201,000 data points looks like on one plot. It's kind of cool. It's a nice thing plot. To calibrate you, on the horizontal axis is a property that relates to how easy it is to put an electron onto the material. So the things towards the left of the plot, towards the right of the plot are easier to put an electron on. And on the vertical axis is how hard it is to take an electron out. So the things towards the bottom of the vertical axis are easy to take an electron out of. So what does that mean? That means the bottom left of the graph is the donors, and then the top right is the electron acceptors. So we know that the parent structure of pentacene is an electron donor. So the structures without nitrogen should lie in the electron donor region. And sure enough, if I zoom in and show you all the structures without nitrogen, there they are. They make the donorest of the donor part. Furthermore, you don't have to be a chemist to notice that there's a striking feature in this plot. There's a diagonal line running right through it. All the structures lie at or below that line. That one-to-one line from reduction potential to oxidation potential is what we chemists call the band gap. It's related to the color of light that these materials will absorb. Materials below the line absorb more red light. So we already see that there's a lot of ways to make pentacene absorb more red and not a lot of ways to make more blue. If you look very closely, though, there are a privileged subset of structures that are kind of making an excursion above that line, and that's definitely something that we're interested in looking into. So, which of these is the best one? If you can tell me, we need to talk afterwards, because I can't do it. I wish I knew. But this is only two data points, this is only two axes, these are only two things. We actually calculated 6 different properties that you can't plot on one plot. And we're trying to come up with an algorithm that's going to weight and sort and compare these against each other with what we think will make a good figure of merit for an organic photovoltaic. That algorithm might change tomorrow when we decide, you know, we were thinking about this wrong. It's different properties that we need to look at. Next week, I might not even want to make a solar cell. I might want to switch it around and make an organic light-emitting diode. These properties are still relevant to that. I don't have to go back and recalculate anything. I can come through and search the data in a different way. So what's the score? Where does it stand? What are we doing in the laboratory? So we've talked a lot about target selection. From that 135-member library, that was kind of the smaller study, we selected 2 molecules and made them in the lab. It took us about 2 years to actually come up with a way to make these. And when we did, we found out we hit a bit of a snag. Turns out when you have a handful of this material, molecules interact with their neighbors so strongly that this is completely insoluble in any organic solvent. It makes it impossible for us to process this into a device. So that was really a roadblock. We can't make a working device out of this material, even though it might be great in terms of its individual molecular properties. So we took that and selected 2 molecules that we're now synthesizing in the lab from the MegaRun. The phenyl groups were included because we think that that's going to help to break up some of that intermolecular interaction and make more soluble materials. We also selected some that we think will make them more stable to air. So these are the things that we're working on. This is where it stands. We're hoping that these will give us, you know, more usable material. We can actually calculate it. There's a way to do it. We didn't do it in the MegaRun. You can take the one molecule that you calculate, put it in a box of many of its neighbors, and then calculate the forces between those molecules. The thing is, this requires an enormous amount of computational resources. This study, if it takes a day to calculate one molecule, it'll take a week to calculate many of them. So I'm just kind of concluding here by leaving this open to the audience. I realize I'm the guy who pushed the button on the MegaRun and we broke all sorts of records, and now here I am saying, I want you all to think of ways to be clever and give us 1,000 times more. We want to do the GigaRun, right? So with that, I'll just kind of, I'll leave it to you to think of ways to increase the power, to give us resources. If you can think of ways of making it faster, we will use it. Thank you all.
Thank you, Patrick. Isn't he an awesome speaker? So how did we do this? I'll talk a little bit about the technical piece, and then I really want to allocate a lot of time for David, because his talk is exceptionally good about increasing throughput on design. A normal deployment for us is a burst deployment. So this is something where you have an internal HPC environment, you have potentially multiple external HPC environments, and you're really doing three things. So you remember that Novartis diagram. Essentially, you might be doing workload placement across multiple different external and one internal, doing data scheduling alongside it, and also orchestrating external environments. This is kind of our normal production cluster, and we've been doing this for a while. The MegaRun, however, is at a much larger scale and entirely external. So it's a radically different design than what we talked about earlier. So it's about 2.3 million core hours to process those 200,000 molecules. Each of those, so 2.3 million core hours, to give you perspective, is about a quarter of a compute millennium. So it's 264 years. That was done in about 18 hours. The total core capacity that we had varied over time. So it took us about an hour and a half to get that 160,000 cores, 156,000 cores. We did it across 8 regions. So we had all the APAC, so Singapore, Japan, Australia. We had South America and Brazil. We had US West 1 and 2, US East, and the UK. All of these up and running and processing part of this workload at various times. So the way this actually looked is you had one of these essentially cells, if you will, in each of the regions. And then you had coordination that coordinated between all of the regions. And within a cell, you have CycleCloud essentially doing the orchestration of everything within that region across all the AZs. We actually wrote a distributed job queue that has a few unique properties. So as opposed to message buses, pure message buses, and batch schedulers, which are really designed to handle either large core counts and small numbers of jobs because they're MPI oriented, or batch environments that have tens of thousands of cores with maybe hundreds of thousands of jobs in queue. Jupyter's actually designed to handle tens of millions of jobs with millions of cores. So our design goals for it were pretty high. We did not get to test 1 million cores. We got to test 156,000, so that's our known scale limit at the moment. And this ran essentially with double resiliency, so there were essentially the queue itself is represented in a way that could survive 2 individual server, AZ, or region failures. And in fact, we saw that in this environment. We actually were not getting the price performance out of Australia that we were expecting, so we actually had that one just nuked it right around this time frame. And Brazil also was not working out at the time as well. So both of these regions essentially got stopped. We didn't do any operation other than kill them. And all of the workload that would have run in those regions basically automatically rescheduled itself somewhere else inside the environment. So this essentially was designed to be very resilient. From a practical standpoint, when you look at this environment, and I like to make the joke that we had to buy everybody Retina displays after this run. But these are all 16,000 of the individual nodes. The red ones, which you may be able to faintly see in the back, are essentially ones that have some form of error that we've identified with them, and we're currently automatically processing that error. The green ones are the ones that are fully processing properly. And we were able to grab a tremendously large amount of core count, basically over the course of about 2 hours, 150,000 cores, and we hit 1.21 petaflops. Which at the time I think was number 29 in terms of our peak on the supercomputing list. So this is a really exciting run. We were very excited about the technical side of it, but the science was really awesome, and that's really why we're all here. So with that in mind, allow me to introduce David Hines, who can talk about essentially mechanical design and computer-aided engineering for hard disk drives.
Thank you, Jason and Patrick. So my name is David Hines. I'm from HGST, and I'm going to talk a little bit about the big runs and whatnot. But what Jason and Patrick have talked about in terms of the MegaRun and expanding into large instances of cloud across the cloud, we're doing that on a little bit smaller scale at HGST, but all around development of hard disk drives. And so I'll go through a couple things here. We'll talk about who HGST is, how we use high-performance computing to develop hard disk drives, where we're at in our journey around cloud computing and high-performance computing in the AWS environment. And we'll talk a little bit also about what we're doing to optimize and refine that environment for effectiveness and cost savings. So who is HGST? HGST is one of the leading vendors of hard disk drives in the world. We are producing hard disk drives mainly for data center deployments such as Amazon Web Services and most other large data center environments are utilizing hard disk drives from HGST. Anywhere from 1 to all the way up to 12 terabyte hard disk drives are coming out of our product line. And most recently, we've developed a product line and released a product line late last year that instead of having air inside of it, it has helium inside of the hard disk drive. And the interesting thing is for HGST to achieve those results and produce hard disk drives with more and more capacity, but the same form factor, which really hasn't changed in the last 5 to 10 years. We're using high-performance modeling and simulation to go find the right designs, to find the right solutions that can be produced and be provided as a product. For HGST, there's 2 main areas that we're using high-performance computing to develop our hard disk drives. The first one is mechanical innovation. Develop drives that are more efficient for cooling, more efficient for power, more efficient for all the different mechanical issues that can be encountered when you've got a rigid form factor that can't be changed. The other aspect that we're looking at for hard disk drives and improving the product is improving areal density, i.e., how can I squeeze more bits into that same space? How do you get, instead of 5 terabytes, you have 10 terabytes or 12 terabytes or more terabytes, but still keeping the same form factor? You have to increase the number of rotating media in there. You have to change how the bits are captured on that rotating media. And it's only through high-performance computing and the modeling and simulation coming off of that can we go after and find those designs that make sense for our teams to build to provide great products to the industry. And so what does that have to do with cloud computing? So we've been working with Jason and the team at Cycle Computing for about 18 months now. We've gone through a couple stages to ensure that we understand how the environment works, how we can use the environment to the best of our ability, and then how to accelerate it. Last year at this time, we had one proof of concept up and running in AWS with the team at Cycle Computing, and we were very happy with the results. Since then, we've actually started and accelerated that. We're now up to at least 4 workloads, if not more. We're actually into the space of now we're looking at how do we optimize ourselves, how do we optimize the use of the cloud computing such that we can actually either put more applications and workloads up there or improve our costs, right? Because what wasn't mentioned before is you want to make sure that as you go through this effort and you understand your cloud computing environment, you're optimized for cost. Unlike universities, which may or may not have a budget some days for their computing, in the manufacturing realm, it's all about how do you produce products faster and how do you produce products for less money. So we're definitely very concerned about making sure that as we go after the development efforts and as we apply the computing capability, it's cost efficient for the development teams at HGST. So what I have here is 4 different workloads. And what I'm trying to highlight here is that by migrating to the cloud-based computing on Amazon, working with the team at Cycle Computing, we've been able to change how the workflow works for the different development teams. The research teams who are used to having a workstation sitting next to them or an on-site supercomputing with a very rigid, fixed environment. They have 100 cores or 100 CPUs, and that's all they have, and they just kind of work themselves to figure out how to most efficiently use that computing so they feel like they're doing their best to utilize the tools that they have at their hands. Like any good development team, any good engineering team, you give them tools, they're going to maximize the tools to the best of their ability. But on the flip side, if we give them tools that are flexible, they can actually change their workflow to be much more efficient. So we have, at least we have the 4 workloads up here that we've been able to significantly impact their simulation throughput. And it all goes back to what Jason said and Patrick said, which is how quickly can I get to figure out which designs do I develop to make the product? And for these teams, across these workloads, we're anywhere from 1.7x to 2x to 4x or more in terms of how fast can they do the compute and figure out which designs to go after. And now our problem isn't so much the compute, is the time it takes to analyze the results that come off of here. You get a big swath of data, and you're like, oh, geez, I got to go analyze that. So it's actually, we're getting more compute than they can handle because they can't post-process the data and analyze the answers as quickly as we can produce the results. One thing I wanted to highlight in terms of using cloud computing, and if you've been using high-performance computing and workstations, on-premise systems, you're used to saying, okay, these systems are running all the time, their compute are running all the time, and that's that. And what we found is that's, as we migrated to cloud computing and put analytics against this and really understanding how the workloads are operating, the workloads vary quite a bit. And that's okay. That's not a problem because with using Amazon Web Services and what they have, you just pay for what you use. So if you look at the one workload on the very upper left, or your upper right, he's running 24/7 all the time. Okay, you pay for that. But the other workloads, they vary. People go on vacation, people go home for the weekends, people go home at night, or they've got big jobs that have to get run over a couple days. And you can shape your compute, you can change how many cores, how many cluster instances you applied towards that problem to get the job done on the schedule that needs to be done, not the other way around. So it provides a flexibility for the teams to get their answers needed on their timeline, not on the timeline of, oh, geez, when is the computer available? So I wanted to highlight two things. One, this is the material that I submitted to the AWS conference last week, and I'll have an update on this. But as we have evolved our use of AWS, we migrated from just on-demand and reserved instances to try and go after using spot instances because those are the most cost-effective use of compute from AWS that we can see today. And we were able to actually be very efficient and shrink down here, as we have highlighted, about 30 days of computing into 5 days. And we were able to do it by only spending about $4,000, a little bit more than $4,000. So the interesting thing here is not that we were able to shrink the compute down or we were able to span it out to a lot of clusters. The interesting thing here is we did not lose any compute nodes during this run. So if you think about spot instances and you look at the documentation, it says, okay, you can start up an instance and you can start your job, and oh, by the way, if somebody else wants that compute instance for a different price, you may lose it. So that was one of the concerns that we had as we went into it, since we better make sure we don't lose any, and actually it turns out we lost none. So over 5 days of running, using the spot instances, doing this massive amount of compute for our team, we lost no spot instances. So what that provides us in our development teams is another tool in the toolkit such that we want to really expand and go after some deep design space and figure out which designs we want to get after. We can expand to a spot use case and use those instances and get the compute done in a very short amount of time for really not that much money. So the next step is, let's go even farther. So that same compute simulation program, we took another large batch of simulations and said, okay, let's go and try and understand how big can we go on an instance in spot clusters and how much can we really impact and shrink down that computing. So instead of shrinking 30 days to 5, we took 30 days and shrank it to 8 hours of compute, which is pretty significant. And again, this is running across the spot instances, working with a team at Stockholm Computing and putting together the different compute capabilities that are presented by AWS. The nice thing is, and it ran over the weekend, actually, I think it was just 1 day we spent getting it to run. It ran on a Sunday, believe it or not, right? Because that's when we put everything together. The researcher came back and said, great, I've got all my results done. Instead of waiting 30 days or 8 days or 5 days, boom, it was done in a day. Came back on Monday, and he's like, great, now I have to go analyze all the results and figure out where I want to point my next set of simulations. So the interesting thing is the researcher is going through results, and he's like, great, I'll be ready in another week for another batch of simulations. Let me know if we can do this again, right, and go after the next design space. So we're very fortunate to be working with the team at Cyclone, finding that this capability for our teams has become very useful and very helpful to get after new designs. The other point I wanted to highlight here is it's important if you do a lot of computing and you utilize the cloud computing space, you want to understand how your workloads are used in the compute environment and then look to try and optimize for costs. As again, in a manufacturing environment, producing products, we're very focused on making sure that we don't go over our budgets. We are effective in using our compute and effective in using our dollars that are provided. So what I have here are two screenshots using Cloudability. And Cloudability is one of the tools that we've been using at HGST to ensure that we understand how the workloads are running across the cloud space, and then how can we cost effectively optimize that environment. So we've just gone through a complete redo of our AWS environment to optimize for using reserved instances, using the spot instances you saw, such that we can get the best bang for the buck, right? And many of my researchers are always concerned, hey, I want to make sure I get the best bang for the buck. What we're doing for them is we're using the right tools to make sure they do get the best bang for the buck. Now, I did blank out a couple things here because I didn't want to highlight how much money we're spending up there, but it's not that bad. But the key thing is that you can save anywhere from 11% to 30% by shaping your compute, changing your environment, and making sure you're using the right compute capabilities that your teams need moving forward. And if you remember, you couldn't do that when you buy hardware that sits on site, right? If it's sitting next to a guy's desk or in a closet somewhere, or even down in my data center, I don't have the flexibility to change clusters, change out instances, and change out cost on a whim. So this is a very powerful tool for our teams to be cost effective as they move forward. So for us, we're about 15 or 16 months in. We're progressing nicely in utilizing high performance compute on AWS. We're very happy. We have more workloads that are coming up every day that we're going to be migrating from on-premise to the cloud. It's going to allow our teams that are in the US and Japan to share compute much more efficiently. Right now, they're actually FTPing files back and forth, and they're emailing files back and forth and whatnot. And we're going to build some very interesting environments for them. So it's very promising about what we can do in the manufacturing realm to provide a compute capability that hasn't happened before. Make sure your teams take the right steps. As I said, we're about 18 months in. We're about at step 4 that I called it, but we wouldn't be successful at step 4 if we hadn't gone through the prior steps of starting small with a proof of concept, getting an app up there, and then migrating out. It's very important to pick the right partners and the right teams to work with. So working with AWS, working with Cycle Computing, utilizing the tools from Cloudability have been key for us to be successful. And you can pick partners, but make sure you pick the right ones to be successful. Otherwise, you'll be going back and redoing things. And then, as we've been doing, continually evaluate your environment, making sure that you understand how the workloads are operating. Are your customers or are your users happy, right? Or do they have new requirements? And how do you want to change your environment to make sure that you meet their needs, but you're also utilizing your resources effectively?
Yeah, thank you, David. That was very well put. Just in closing, we have time for about 5 minutes worth of questions. I just wanted to employ everyone here that's either enabling users or is a user of technical computing. Think big, think of the right question. Don't limit what your thinking is to what the infrastructure is, because you really don't have to anymore. And regardless of whether or not you use our stuff or you're writing your own code to do things on AWS, the capacity is out there. You can take advantage of Spot. Please ask the right questions, get answers, and go invent and discover. So with that, I'd love to take any questions that anyone has. I think we have time probably for about 2. And Patrick and David and I are happy to what you may have. Sure. Yeah, we do have GPU workloads that have run. We actually published the first, we had the first production cluster, I believe, on the CG1s back in 2010, so we do fully support those instance types with GPU. G2 has some quirks to it, but it's a great instance type from a practical standpoint. I hope that answered that question, please.
Yeah, how do you go about spinning up so many instances? I noticed that
Yeah, it's a hard problem. So to be fair, since 2008, we've probably spent I'm a bootstrap software company, but we probably spend about 15 million in revenue on engineers that write that. It's 125 man years thereabouts in the software. So it's a lot of issues. So you have everything from rate limiting requests to figuring out, all right, well, if the software distribution is 20 gigs and my EBS volume is this size and I have EBS limitations that I have to work within, then how am I going to actually get the code onto the boxes in the right way? There's all kinds of problems that kind of crop up, and I guess the only answer is you have to beat your face into the wall until you fix them and answers pop out. So we really have just spent a tremendous amount of time kind of dealing with the instance request side, dealing with error handling, dealing with the security requirements of a lot of the customer base that we have. They're pretty stringent about 30-page Excel spreadsheets on how encryption works and blah, 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 and just kind of pounding through those answers. In terms of some of the detail, Rob Futrick's in the back. He's our CTO, and although I am somewhat technical, he's very technical. You can put your hand up. Again, please feel free to ask him questions after the session. Any other questions for David or Patrick? All right, well, even with all the interruption, we're finishing 2 minutes early. This is awesome. So thank you guys. Have a great day.